fundamentals of electricity and electronics. Today we are going to see about the unit 1, which is titled as electrostatics. Before going into this, let us know about what is electrostatics. Electrostatics is a fascinating branch of physics that deals with the study of static electricity. It is a kind of electricity that doesn't flow like current in our electrical appliances. Instead, it remains stationary, creating mesmerizing phenomena like lightning, static shocks, and the attraction of materials. Electric charges are tiny particles found in our atoms, like protons with a positive charge and electrons with a negative charge. In electrostatics, we explore how these charges interact and they influence the world around us. Coming to the law of electric charges, the law of electric charges follows the simple rule. Electrostatics will follow a simple rule which was formulated by Charles Augustin de Coulomb. Okay. This law states that the opposite charges interact each other with a force that is directly proportional to the product of their charges and inversely proportional to the square of the distance between them. Like if let us take q1 and q2 are two opposite charges which are separated by a distance small r. Okay, then the force of attraction between the two charges, like F is directly proportional to q1 q2 and inversely proportional to the square of the distance between them, that is r square. So F is directly proportional to q1 q2 by r square. This is called as the law of electric charges. Coming to the electrostatic force, when charged objects interact, they experience an invisible force called the electrostatic force. Okay. This force can be strong enough to make objects move, as seen when you rub a balloon on your hair or create sparks by shuffling your feet on a carpet. Understanding this force is crucial to various real world applications, this electrostatic force, including the functioning of electronic devices and the behavior of lightning. Coming to the applications of electrostatics, electrostatics has numerous applications in our daily lives. Let us take the examples of photocopying machines use electrostatic principle to make copies. Okay. In air purifiers, we use static electricity to remove dust and particles from the air. In order to separate dust and particles, we use this electrostatic phenomena. And in spray painting involves electrostatic spraying to get an even coat of paint. In order to get the even coat of paint, electrostatics are used. And popular application is Van de Graaff generator which create high voltage static electricity, which are used for scientific experiments and demonstrations. And the next one is lightning rods. Lightning rods help protect buildings from lightning strikes by safely directing the electrical charge to the ground. They will direct the electric charge to the ground. Coming to the importance of electric charge, electricity is a fundamental force of the nature. Electric charges are tiny particles found within the atoms, and they can be either positive or negative. The charge may be either positive or negative. The importance of electric charges cannot be overstated. They have many technological advancements and conveniences that we enjoy today. Coming to the creation of electricity, electric charges are the important phenomena. The importance of electric charges, they will create the electricity. Electric charges are the building blocks of electricity. When electric charges are in motion, we get the electric current. When only the charges move, then only we'll get the current. This current is what powers our homes, lights up our cities, enables our gadgets to function. Without electric charges, there won't be no electricity, and our modern world will come to a standstill. Coming to the static electricity, the importance of electric charge, it is one of the important of electricity. Have you ever rubbed a balloon against your hair and seen it stuck? Yeah, that's static electricity. Static electricity caused by the transfer of electric charges between objects has been, various practical uses. For example, it's used in printers to stick toner to paper, and in industrial process to remove, dust from surfaces. And the importance of electric charges is electrical appliances. The devices we use every day, like smartphones, refrigerators, televisions, all rely on electric charges. Inside these applications, electric charges flow through circuits to perform various functions. The ability to harness and control these charges has made our lives more convenient and efficient. The other importance of electric charges is medical applications. In medical applications, electric charges plays a significant role. Uh, Electrocardiograms and ECGs, you well know. No? ECGs and EEGs are medical tests that measure the electrical activity in the heart and brain, respectively. Respectively, these tests helps doctors recognize and treat various conditions. Coming to the other important importance of electric charge is renewable energy. Electric charges are essential for harnessing renewable energy sources like solar and wind power. Solar panels and wind turbines, they'll convert the sunlight and wind energy into electricity through the movement of electric charges. By with their movement, they will convert. This helps reduce our reliance on fossil fuels and environmental problems. Coming to the one of the importance of electric charges is in the field of communication. The internet, smartphones, television all rely on the transition of electric signals. The signals carry information in the form of electric charges, allowing us to communicate, browse the web, and watch the entertainment. Without electric charges, global communication has, as we know, it would be impossible. The next one is the Coulomb's law. Coulomb's law is described as the, as I said, F is equal to force of attraction between two charges is Q1 Q2 by R square, where R is the distance between the two charges. F represents the force of attraction or force of repulsion. K is called as the Coulomb's constant, and Q and Q2 are the magnitudes of the two charges. R is the distance between them. Now this equation shows that the force is directly proportional to the product of the two charges like Q1 Q2, and it is inversely proportional to the square of the distance between them R. The greater the charges and the closer they are, the stronger the force is. If the distance between the charges is more, the force of attraction between them this will be less. Coming to the implications of Coulomb's law, the first one is force increases with charge by its magnitude. If you increase the magnitude of the charges, the force between them becomes stronger. For example, two electrons which are negatively charged will experience a stronger repulsion than an electron and a proton which are oppositely charged. This is what force increases with charge magnitude. Force decreases with distance. As the charges move apart, the force between them weakens significantly. This is why you can pick up a piece of paper with a neutral piece of plastic. The attractive forces are too weak to overcome the force of gravity. The next implication is electrostatic interactions. Coulomb's law is responsible for all electrostatic interactions, including the behavior of materials like plastics that become charged when rubbed. These interactions also underlie. Next, coming to the practical applications, Coulomb's law is not just a theoretical concept. It has real world applications in electrostatic, electric motors and generators, and particle accelerators. Electrostatic precipitators used in the industry to remove dust and pollution from air by exploring the electrostatic charges. And coming to the electric motors and generators, the motion of electric charges create electric currents which are harnessed in devices such as generators and motors. Now coming to the particle accelerators, which are used in cutting edge physics research to accelerate particles to higher speed. Coming to the statement of Coulomb's law, it was named after the scientist Charles Augustin de Coulomb. This law provides crucial insights. It tells about the behavior of charged particles, whether they attract or repel each other, and strength of the interaction. This is what about the Coulomb's law equation, as you have seen that, but K is called as the force constant, which is given by 1 by 4 pi epsilon naught, where epsilon naught is the permittivity of free space. Okay, epsilon naught is the permittivity of free space. F is the force of attraction between the two charges Q1 and Q2. K is called as the Coulomb's law constant, and R is the distance between the two charges Q1 and Q2. Now coming to the inverse square law. The Coulomb's law that it follows, the Coulomb's law will follow the inverse square law. This means that as you double the distance between the two charges, the force between the two charges decreases to 1/4 of its original strength. Okay, if you double, it will decreases to 1/4. Conversely, like if you have the distance, the force, if you have the distance, the force increases, the force will increases. This principle demonstrates the remarkable sensitivity of electric interactions to distance. Coming to the next one, direction of the force. Coulomb's law also provides the information about the direction of the force between the two charges. The force acts along the line joining the two charges and is attractive if the charges have opposite signs, which means that one is negative or the other one is positive, and repulsive if they have the same sign, like if both are positive or if both are negative. Coming to the unit of charge is coulomb. No, it is coulomb. 1 coulomb of charge represents a substantial amount of charge equivalent to the 6.24 into 10 power 18 electrons. Coming to the electric field is a fundamental concept in physics that helps us understand the behavior of electric charges. It plays a crucial role in our daily lives, from powering our electronic devices to the natural processes that occur in the real world. What is meant by electric field? Electric field is the invisible force. Here you can see the invisible force that surrounds the electric charge, whether it is positive or negative, whatever it may be. The field around the charge is known as the electric field. It is the property of space that describes how these charges interact with each other. Imagine it as an invisible net that surrounds charged objects, influencing other charged objects nearby. The next one is electric field. How does the electric field work? The electric field is created by electric charges. When a charged object like a positively charged proton or negatively charged proton is placed in space, it generates an electric field around it. The force can either attract or repel or changes depending upon whether they have the same or opposite charges. Like charges will repel and the opposite charges will attract. It's the same principle. And coming to the measuring of electric field, scientists use a concept called electric field lines to visualize and measure the strength and direction of the electric field. These lines point away from positive charge and towards the negative charges, showing the direction is a positive test charge would move if you place it at a particular point in the field. The practical appliances of the practical applications of electric field is in electronics. The electric field is the driving force behind the flow of electric current in wires, enabling the operation of electronic devices like smartphones. They are also used in electric motors. Electric motors use the interaction of electric fields to convert this electrical energy into mechanical energy. Coming to the lightning is a natural process of electric energy in the atmosphere, that causes by building up of the electric fields. and in everyday life application we use this electric field. Coming to the definition of electric field strength is simply referred as the fundamental concept. It is a fundamental concept which simply says that electric field is the strength as a force experienced by a positive the force experienced by the positive test charge placed at a specific point in a space divided by the magnitude of the test charge itself. It is represented by a letter E. Then coming to the mathematical equation of this electric field strength, it is denoted by E is equal to F by Q, where we know that F represents the force experienced by the test charge and Q is the magnitude of the test charge, where E represents the electric field strength. Now coming to the electric intensity. What is this electric intensity? Electricity is a fundamental concept. We know that electric intensity is often referred as the electric field strength. Is a measure of how strong an electric field is at a given point, which means that it determines how strong it is at the given point. An electric field is a region around an electric charge whether the charge's opposite experiences a force. Imagine that electric intensity as an invisible lines that surrounds the charged particles. These lines indicate the direction and strength of the force. And how this electric intensity is measured? Electric intensity is measured by the formula E is equal to F by Q, where E is the electric intensity and F is the force. Then what is the significance of electric intensity? They are used in safety purposes. Understanding electrics, it helps engineers and electricians design systems that prevent electrical accidents. And the other significance is in technology. Electric intensity, it enables controlled flow of electric current through circuits. And the next one is renewable energy. Renewable energy sources like solar panels, winds, turbines, electric intensity. In these applications, electric intensity important for capturing and converting energy from sunlight and wind into electricity. And the other important aspect is in medical field. Electric intensity are used in medical devices like electrocardiograms to monitor and diagnose health conditions. In order to diagnose health conditions, it plays a vital role. The next one is electric potential. Electric potential is a measure of electric charge per unit area at a specific point in an electric field. Think of it as a sort of push that electric charges experience in an electric field. It is represented by the letter V. The higher the voltage, the greater the push. The lesser the voltage, the lesser will be the push. They are directly proportional to each other. Coming to the electric field outside the charged conducting sphere. Let us consider a charged conducting sphere where the charge is spread all over the sphere uniformly. Before deriving this, let us briefly understand what an electric field is. Electric field is the region or space around that object. And what is meant by this conducting sphere? A conducting sphere is a spherical object made of a material that allows electric charges to move freely within it. When the sphere is charged either positively or negatively, the charges redistribute themselves equally on the sphere. This is what about the electric field outside the sphere. Then coming to the equation or the electric field outside the sphere. Mathematically, we know that the electric field strength or electric field is inversely proportional to the square of the distance, where r is the distance from the center of the sphere to the point where we are going to find the field. It is inversely proportional to the electric field. Let us focus on the electric field outside the charged conducting sheet. This concept is described by Gauss law, which states that we know that the electric field at a given distance is directly proportional to the net charge enclosed within the sphere of that radius. The next topic is about the electric intensity and potential due to the uniformly charged sphere. Uniformly charged sphere. Electricity is a fundamental concept that plays a crucial role. When we study electricity, we often encounter the concept of electric intensity and electric potential. Imagine a perfect sphere made of conducting material such as metal. We distribute electric charge evenly over the surface. This means that the charge is spread out uniformly in all directions. Electric intensity, we know that it is represented by the letter E, where E is the electric intensity, Q is the total charge on the sphere, and E is the permittivity of the free space, and it is a constant, and R is the distance from the center of the sphere. The next one is the electric potential. Electric potential is denoted by the letter V. It also will have the same phenomena, like V is the electric potential, K is the Coulomb's constant, as you have seen earlier, and Q is the total charge on the sphere, and R is the distance of the sphere. And the last topic is about the electric field inside the conducting sphere. An electric field is invisible through that surrounds electric charges. It push or pull on the electric charges placed in its vicinity. Think of it is invisible net. Think this as invisible. Net charges conduct is spread all over the sphere throughout the sphere uniform.